See, those who have not yet received any invitation emails to this session, let me know your email ID, the one which you regularly use to join the classes. Okay. See, let us begin with this lecture. What today we are trying, if you recall our last lecture, the lecture before yesterday, we saw linear regression using scikit, right? And what we had discussed then was we said that instead of using pre-implemented linear regression algorithm, we will write our own linear regression implementation, right? So I said that we will write and we will do all that by our own, by writing our own Python code. But before we move to that, we need to understand how is an error is measured for a specific machine learning model. So when we are talking about error, see, if we do not know how to measure error, there is no point in doing machine learning, because machine learning is nothing but it's a gradual improvement in error margin so that I can fit that curve to an expected level of performance. So during training as well. So if okay, so if I ask you in some other words, if I put a general question to you, when I am training my machine learning model on a data set, when should I stop the training? Let me see. So just respond in chat window to my question. The question is, when should I stop training the ML model? Because training is effectively, I can repeat it for virtually for eternity, right? I can always keep on repeating training, but a ML model or the ML engineer has to know, or that a algorithm developer has to know at what point the training has to stop. So can you guess at what point I need to stop the training? For example, if you recall our code, linear regression code, I think, let me see if I can open. To recall our linear regression scikit code, we have used model.fit, right? If you recall that, let me see if I can open that. We have used model.fit, and what I told you is model.fit trains on that data set. Now, a very important question arises is, when will that training stop? So what I said is that model dot fit, what are the line which you see here? This is what you're providing. You're providing your data set, X train and Y train. It is training to fit a linear regression curve, linear regression line. So when would training stop? When has to the training stop? So let us forget about right answer, wrong answer, anything. When you're training on that, for example, let us keep machine learning aside for a time being. You are trying to become a good chess player, right? You are trying to become a good chess player. You want to play various competitive chess games. So you are learning chess. At what point you will stop training the your ability to play chess? So it's very important that I strike this thought in your minds. Only then it makes sense uh, to implement this linear regression program on our own. Because see, if when we implement this program on our own linear regression, I as a developer need to know when should I stop the training. Yeah, so can you all respond, students? Like whenever you're working on any task, let us forget about machine learning. You're trying to learn a new skill. When should you effectively stop your training? And I hope you all have even started learning Python syntax and everything. There was a point where you stopped learning Python, and you started practicing Python more. What was that point? At what point you stopped learning Python programming as a new language, and you started practicing on your own? What was that point? Can you say that that point will be same for each and every student who wants to learn Python? So, see, I just want to initiate a small discussion. You can discuss in chat window. So, my question is, when should you stop training, or what factors should I consider based on which I can decide if I need to stop training or if I need to continue further? Let us discuss about affecting factors. There could be many factors. You can list out each and every factor, and then we can decide what exactly is the right answer. Yeah, I get one response when they say that when performance starts to degrade. Okay, one good point. The next response I get is when I think when we learn all requirements. Okay, anything else? When we get output as per our requirement. Okay. Anything else? See, when to stop training, as I said, like you are learning to play a chess, and when to stop, it depends upon person to person. Likewise, when to stop training machine learning model, it depends upon context. But during in our course, what we will look at, we look at some of the factors which are responsible for making us or arriving us at a decision to stop the training. The first and most important thing is, now, when I said this is a linear regression, I also told you that whenever we go with this, like whenever we move with linear regression, I always have something called as error curve. What I told you is error curve, right? So I told you that initially error is high, and then it might drop, it might increase, it might drop, and it might increase, right? So every learning algorithm has an error curve associated with that. So see, this could be for linear regression. For some, it could be this way. For some, it could be this, right? So I have three curves. This is one, this is two, and this is three. So every learning model has its own error curve. So when we want to develop a machine learning model, I want to develop a machine learning model which is most accurate possible for that given data set. And when would be the machine learning model will be most accurate for a given data set? When it has the least possible error curve at a point where it can reach. So that's the maximum accuracy it can achieve for the given data set, considering a lot of other factors like what the data set includes, what kind of prediction and all that. So it is for one and this is for two. So usually all your pre-built algorithms, they stop at a point where their error curve has the least value. That's the point where we stop training that. If you train beyond this point, there will be no improvement in error, rather you will be going towards overfitting, which leads into high variance as well. Right? I hope you're getting that. So, in order to stop the training, I need to reach to a point where my ML model for that given algorithm has the least possible error value for that. Okay? See, this is the most generally accepted practice. For some specific model, you might even stop at this point. So, this is your expected for the domain. Technically, it reaches to zero error level for this curve, but considering that domain, maybe it is for some stock market or something, you only expect 5% error margin, and that is fine for you. So you can even stop for that, but these are very rare. We always try to reach to the minimum point possible for that learning model. So here, in order to stop our training, we need to know when we have the least possible error for that module. Now we are saying that this is error model, this is error curve, and that. But see, on x-axis, what we plot? We plot number of training samples. What we plot here? Number of samples, right? And on y-axis, what we plot? We plot something called as error metric. What we call? We call it as error metric. And error metric are different for different kinds of algorithms. So for linear regression, it could be some value. For classification, it could be some value. For clustering, it could be some value. So it depends upon what model and what kind of learning we are doing. We know the as and when the number of samples increase and decrease, we know this. Fine. Or it could be number of training epochs as well. See, I wrote here samples, and it could be even epochs or a number of iterations across the training sample as well. So it could be various measures on this x-axis. And here on y-axis, we always plot the error metric. Now we have to understand for a linear regression, what would be this error metric? For example, if I'm doing a classification task, what would be the error metric? So that's what we are going to learn in today's lecture. What are the error metrics in machine learning? So in for today's lecture, we will try to just get introduced to this error matrix, and we will look at details of this in next lecture. So now coming back to the linear regression, let us suppose this is my linear regression, and these are the data points. The crosses are the data points, and the curve which I have plotted is the learned linear equation or linear curve, the regression curve. Fine. So to this linear curve, can you tell me how would you calculate the error? Remember, this curve here is not covering all the data points. Remember, not every data point is falling on this curve, but it is trying to fit into the behavior of these points. So I want to find out what is error value associated with this linear regression curve. Now, before I discuss, before I come to actual point, how we calculate error or what should be the error for this point, can you tell me? Okay, instead of asking, let me tell you. So if I want to find out error, so what is error? The error is I have expected value and the predicted value. For, let us suppose, okay, let us suppose here for this point here, for this point, this is expected value, right? And this is something I got a predicted value here at this point. Now if you see here, let us suppose this is x is equal to 5, and here let us suppose these are 1. Forget, I'm drawing a straight line, just forget about this drawing. So expected value I got is 4, and expected value is 4.5, right? And the predicted value which I got is 4. So what is the difference I have here? The difference is 0.5, right, for this point. Likewise, if I consider this point, for example, when I come to this point here, it is say 3, and the actual value, the predicted value is around 3.5, right? It is 3.5. So what is difference here now? The difference between expected value and predicted value. What I'm taking? Expected value minus predicted value. This is what I'm taking. If I do this here, what I'm getting? 0.5. This is what I got this. But for this point here, what I'm getting? Can you type that? What will be the difference? The difference will be minus 0.5. Right? Expected is 3. 3 minus predicted is 3.5. So likewise, when you do it for every point, right? So you calculate something for this point, this point, this point, every point you will do this one. So what you get is you get some values: minus 0.5, plus 0.5, 2, plus 2, minus plus 2, minus 2, plus everything, right? So when you get such all these values, how do you combine these values? How do you combine these individual differences here so that you will get one single value which indicates error behavior of entire learned linear equation? What would be that single value? Can you guess? So you have three options. Let us suppose first one, add all these values which you get. First one, let us say first option is add all the values. Second option, take average of all values. Three, I'll say that something different I need to do it. 1 and 2 will not work. I need to do something different. So how many of you say what would be the right option if I want to get a good measurement of error for this linear equation? Should I do a just addition of all these differences? Should I take average of that? Or you feel that no sir, something different we have to do, plus and average will not work? What is your response for this? Okay. Mohrish says that we have to do an addition. Any other? I hope you got the context what I'm asking. So I need to measure the error associated with the learned linear regression curve. So in order to measure what I'm doing, I'm taking the difference between the predicted value and expected value. And these differences could be positive, negative, positive, negative. But I cannot say I need to talk to people by taking one single value. So I am asking you, what should be the single value? What should be the value? How should I get to that single value based on the differences between expected and predicted values I get? So I have given you three options. Should I just take addition of all the values differences which I get for each data point? Or second option, take an average of these differences and tell that the average is so and so? Or third one, I'm asking that something different I need to do. It should not be plus, it should not be average, but it should be something different. So what would be the best value to get a single measurement of all these differences, expected minus predicted for each data point? That will give me a good indication of how accurate the learning curve was for this given data points. I mean, learned regression curve. Mohorish is saying that addition will do. So if I consider addition, let us suppose I have few points here which are to the above. What they will give you? They will give you positive differences. The points below this line will give you negative values. And the points on this line, they will give you zero values. So now you take addition of this, what would be the final value? The final value is this positive values will cancel out with negative. So you get some value like 0.1, or maybe you may end up with zero value as well. Is it a good description of accuracy of this learned linear regression curve? Just addition. Can I get responses? See, have you understood my question? Let me know if you have not understood the question, because these are something fundamentals. Like we need to understand this. I'm not seeing responses, so I'm a bit skeptical if you have understood it or not. Okay. Anyone else? I don't see responses from others as well. You also have ISC today, or like what's the issue? Okay, so let me tell you what exactly it is. I'm not getting responses today. I'm not sure what's the reason behind this, but let me tell you what is an expected value for measuring the error single value for this error. If you do an addition, remember it will just cancel out addition values, it will cancel out, and it might not give you the perfect description of error associated with this learned regression curve. The same would also go for average, because average is nothing but sum of all but divided by n samples, but it will not also. So we need to do something different. This different, we have two values. What are those two values? The two values are called as the two error metrics for linear regression. The first one is the first one is mean. Okay, we call as mean absolute error. The second one is mean SE. Can you guess what S stands for? Can you at least type this? What S stands for? S stands for squared. So what we do is when we say mean absolute error, we still take average. So what we do is we take, let me write it here. So we take differences, right? So what we do is I take average of all the differences divided by n samples. So what I'm taking summation of all the differences by n. But what I'm doing is I am taking the absolute value. I hope you know what is absolute value. So I do not take into account whether it is positive difference or negative difference. I just consider the difference. So this is called as mean absolute error. So I take absolute value of differences between this point, and I take mean value of that. This is one metric, mean absolute error. The second is what I do is instead of taking just difference, instead of taking absolute values, what I do is I take square of this difference. As you all know that whenever I take a square of differences, whether it is positive or negative, it's always positive. So the second one is squared difference. What is the difference you get? Square it and take the mean value of that. So from 1 and 2, both are usually a good single value which represents the error associated with the learned regression curve. But mean squared error is more famous, and we use it very frequently when we want to do linear regression on our own. So when we will write our own algorithm, so here the number of samples are there. So on y-axis, what we will plot is, we will plot the value associated with mean squared error. So we plot MSC. So at some point when you're learning through data sample, the mean squared value will be the minimum possible. And this is where we will be stopping. So our own algorithm, which we will be implementing in the next subsequent lectures, we will stop at this point for linear regression. For classification, right, this is a linear regression, but for classification, uh, this will not work. The mean squared error, then this absolute error, this will not work. We have a different way of measuring error associated with classification task. In short, I'll give you a clue of that. We use a concept called as confusion matrix for classification. And what exactly is this? How it works? How do I interpret the confusion matrix? It itself is one. It demands one additional lecture in its entirety. So we will discuss that in another lecture where we will talk about how to define the error associated with a classification task. But it's based on the concept of confusion matrix. So if you're curious enough, you can go through the concept of confusion matrix. I think the best explanation of confusion matrix is you will get it on Wikipedia. That is enough for our needs. And those who have already gone through data mining or BI, they might be already knowing what exactly is a confusion matrix. But still, we will explore that in the context of machine learning, specifically in the context of writing machine learning algorithms. So, have you understood this? Have you understood why just taking addition is not enough? Just taking average is not enough. Whenever we are working on linear regression kind of ML tasks, the error values, the way the error value is represented and computed, it has to be by either mean absolute error or mean squared error. Now, there is even a technical reason why we do not prefer mean absolute error and why we prefer mean squared error, but I think that will go very deep into the concept. If some student has this question, sir, why not always rely on mean absolute error and why we always go for squared error? If they are interested, you can put a message in Telegram. I'll discuss there. Okay. So have you understood? Okay. So you also have a ISC today. Okay. Okay, fine. So I think that's it for this lecture. I think we are already running out of time, and the remaining concept, I don't think I can cover confusion matrix in remaining few minutes. So in the next lecture, we'll talk about confusion matrix, or else I'll share some good video on confusion matrix, which will reduce our time and which we can more spend more on this. So in next lecture, what we will do is we will now jump into writing our own linear regression algorithm, and it's the same that will be used as assignment 1 for you. I hope you have gone through the assignment list on Moodle. Did you go through that? On the Moodle where you attempted ISC, there is an assignment list. Go through that, you will understand what assignments you're going to solve there. And assignment 1 is what I'm going to solve it for you. You have to just put it in your own words in the journal or whatever the document you will be submitting at the end. Yeah, and the ISC, I have put that ISC assessment into assessment phase. So you should be in a point to start evaluating the answers based on the discussion we had yesterday. You have time till Saturday 3 p.m. Make sure you assess all. I think each student is getting five students to assess their responses. Complete it by Saturday 3 p.m. and then we will discuss the grades in our next lecture. Okay. So I am fine to end this session. Just mark your attendance and you should be fine to leave this session.